Hello everyone and welcome to the worksheet 20 video key. All right, so we are working on some more alkene addition reactions in today's worksheet. And this is just a summary of the models that we discussed in worksheet 1 and the two different ways of drawing syn and anti-products, either keeping the new groups in the plane or bringing them, putting them on a dash or a wedge, depending on syn and anti. So that's something we just want to keep in mind as we work through the new reactions today. Okay, we're going to start off with Markovnikov hydration with possible rearrangement. So recall that when we use hydronium ion or sulfuric acid in water, that we are going to do Markovnikov hydration of an alkene. And because it goes through a carbocation intermediate, there is the possible potential for rearrangement. When we are thinking about stereochemistry in regards to if two stereocenters are formed, then we want to note that this reaction provides both syn and anti-products through a pathway that doesn't differentiate, and so therefore we get both syn and anti-products. But again, that would only matter if we were generating two stereocenters. As always, sometimes we aren't generating any stereocenters, in which case we wouldn't need to concern ourselves with stereochemistry. If we are generating one stereocenter, then it's always a racemic mixture. All right, so the first thing that it's asking us to do is fill in the curved arrows, show the mechanism of the reaction in scenarios A and B. So the first step, just like the hydrohalogenation reaction that we discussed last time, is a proton transfer. We'll draw our arrows to transfer a proton from hydronium to the pi bond on the alkene. And the arrows are drawn the exact same way. The difference is where the hydrogen is placed, on either the more substituted carbon or the less substituted carbon, which is the difference between A and D. So we can actually take note of that. That will help us later, that this is a tertiary carbocation and this formed the secondary carbocation. And we could also write down some notes that this is a proton transfer step. All right, next it looks like we have nucleophilic attack. The water now can attack the resulting electrophilic center. So this is then a nucleophilic attack. That results in an oxonium ion, which is still a charged intermediate. And so we still need to do further work to get to a neutral product. So the last step looks like they've drawn in water for us so that we can nicely show a final proton transfer. Now you might be asking yourself, well, couldn't this secondary carbocation have rearranged? And the answer is yes, but if it did so, it would have just formed A and then continued with this pathway. All right, so those are the arrows. The next question asks us about the hybridization and shape of the intermediate carbocation. How will the hybridization and shape of the intermediate carbocation affect the structure of the final product? Well, that depends on the number of stereocenters. So let's actually look and see what would be our final product. Are we going to go through the more stable tertiary carbocation or the less stable secondary carbocation? Definitely the more stable tertiary carbocation, A. And therefore, the major product is actually going to be C, right? And in C, we did not form any new stereocenters. So this just has two hydrogens. It is not a stereocenter. And this is also not a stereocenter because there's only 3 different groups attached to that carbon. So to answer this question, right, what we'll say is that, of course, right, carbons that are positively charged, which we call carbocations, are sp2 and trigonal planar. And nucleophiles can approach from the top or bottom face with equal probability. Right? The major product does not have any stereocenters, also known as chiral centers. So we do not need to consider stereoselectivity. Okay, so what would we expect to be the major product? Definitely C, right? Because it's a lower energy pathway going through the more stable carbocation intermediate. All right, let's look at the next page. Question number 6. Consider the mechanism of the following transformation. So that probably means draw the mechanism, although I didn't expressly say that. But let's go ahead and work on the mechanism here. So we have proton transfer, right? This is hydronium ions. This is going to be an acid catalyzed hydration reaction. And it's going to go through a carbocation intermediate that could be subject to rearrangement. So we should be careful when drawing out this mechanism. So we're going to do proton transfer first. Write that in. Recall that that's going to happen selectively to form the most stable carbocation intermediate. So the hydrogen will end up on the less substituted carbon, and the carbocation will end up on the more substituted carbocation. So this is a secondary carbocation, so we should always consider rearrangement. And in this case, it does look like this is a rearranged product, so we need to go ahead and show that rearrangement. We'll draw in the hydride shift. To get to a tertiary carbocation. Now we're ready for the nucleophilic attack. Water is present in this reaction mixture. So when I need it, I can go ahead and draw it in. And now I'm going to show the nucleophilic attack. Go ahead and label this step. We're still not done. We need to do a final deprotonation. So we'll draw in another water molecule. In this case, act as a base and do a final proton transfer. All right. Let's look at the next reaction here. This one is somehow going to be forming a ring. So that's probably not something you've seen before, but if we use all the logic that we've been learning about with these acid catalyzed hydration reactions, we surely can figure out how to make these products. So what is the first step in an acid catalyzed hydration reaction? Well, we just did it before and we showed proton transfer occurring first. So the pi bond attacks the hydronium ion to pick up a proton. So we're going to selectively put that hydrogen on the less substituted carbon in order to form the more stable, in this case, secondary carbocation. But we can actually do that and draw that in such a way that it starts to kind of resemble these rings. So what I'm going to do is draw it this way so that it starts to look like the ring. So we have a 1, 2, 3 methylenes before the positive charge and one more carbon. So 1, 2, 3 methylenes. Coming up, we'll have the positive charge and another methyl group that has taken on a hydrogen, which you can choose to draw in or not at this point. Remember that this carbon, right, is sp2. And the nucleophilic attack occurs from both bases, which is what's leading to the two different stereocenters being formed. Now, whenever we form a carbocation, especially in a secondary carbocation, we should always consider rearrangement. But in this case, there will not be a rearrangement because we cannot form a more stable carbocation with one shift. It's always good to consider that, though, whenever you're forming a carbocation. Forgot to label this, so I'll go ahead and write in proton transfer. Right, and then remember that the next step is nucleophilic attack if there will not be a rearrangement. Go ahead and label this. Okay, so because the attack occurred from both faces, we end up with both stereocenters at the carbon that was substituted. So we just need to do our final proton transfer to get to the products. So we just want to draw in water to show that final proton transfer. And that leads to the two products, plus some hydronium ion, which is just a byproduct that we don't really need to draw in. However, I will label this final proton transfer step. So assign RNS stereochemical configuration at the indicated carbon. Okay, we can do that. We have 1, 2, 3. So 1 to 2 to 3. The fourth priority group is our hydrogen that is pointed back. So clockwise is R. Right? And note that that does not change. So this carbon did not change configurations because it was never a carbocation. Right? So that carbon did not react. Okay. Let's go ahead and predict the product of the following transformations. So it's just looking at the major product. So whenever you do these problems, I really want you to approach it with a multi-step process. The first process, you ask yourself, what is getting added across the double bond? Let's go ahead and practice this. So the first question, what is getting added across the double bond? And the answer to that is when you see H3O plus or H2SO4, the answer is H and OH, right? Which overall is water, which is why we call this a hydration reaction. The next question is, do we need to consider regioselectivity? We'll just kind of simplify that as regioselectivity. Okay. By the way, if this was the same group, like H and H or OH and OH, we would not need to consider regioselectivity. So the first thing we need to do is ask ourselves, are we actually adding two different groups? In that case, we might need to consider regioselectivity. It depends on the substrate and whether or not it's symmetrical. Okay, so this one is not symmetrical. So the answer is yes, we need to consider regioselectivity. Whereas this one is symmetrical, so we do not need to consider regioselectivity. So I'll just come over here and sort of draw a line. Okay. So we'll put, do we need to consider regioselectivity? Well, the answer is yes, only if the two groups are different. And they are, right? So H and OH are different groups, right? And the alkene is not symmetrical. Right? So in some cases, yes, we would need to consider regioselectivity because it's not symmetrical, right? And I'll write no regioselectivity, yes and yes to regioselectivity. So in that case, we want to think about, okay, which carbon is going to get the H and which carbon is going to get the OH, right? And so we're going to go H and OH, and this is going to be following Markovnikov regioselectivity, which means you want to put the OH on the more substituted carbon. All right, question number 3. What about stereoselectivity? That depends on how many stereocenters you're forming, right? So no if forming no stereocenters. We'll put 0 stereocenters. No if you form 0 stereocenters. You don't even really need to consider it for one stereocenter, except for you do want to remember to draw a racemic mixture. Right? So we'll do 1 stereocenter will always equal a racemic mixture, no matter which reaction we're talking about. Right? And then if you have 2 stereocenters, then you need to ask yourself, is this reaction syn, anti, or does it give both? Right? And in this particular reaction, it gives both. So we are not syn or anti-selective, right? It would give all possible stereocenters. We can indicate that if there's 2 stereocenters by showing all 4 stereoisomers, or just drawing single lines to indicate that all stereocenters are formed with little stars. All right, so let's go ahead and draw in products. We said that the OH is going to go on the more substituted carbon. That is the regioselectivity in this case. Are we forming any stereocenters? That is the next question, right? So we are forming, this will get an H, it will not be a stereocenter. This will get an OH, and we will get a stereocenter, right? So we're forming 1 chiral center. We want to make sure to draw a racemic mixture. This case, right, no stereocenters. We'll just label that with S. Right? I'm just going to call regioselectivity big R. The stereoselectivity would be S. No stereoselectivity. 1 stereocenter. Here, hydrogen will go here, OH will go there. That will become, oh, and however, though, we do need to also, in this case, consider rearrangements. Really, this one is not going to happen in all cases, but in reactions that form a carbocation, we do also need to ask ourselves about rearrangement. So we'll put number 4, rearrangements. Right? In this case, we do need to consider rearrangements because this is a reaction that goes through a carbocation intermediate. But yes, as carbocation intermediate. So this secondary carbocation will not rearrange. This secondary one would not rearrange, but this one will rearrange. So we are actually going to get a shift of this methide group. So that's going to be important. And then we're going to, so then the OH group will end up here. So this will be methyl OH, ethyl, and isopropyl. So we will get a stereocenter. So we do want to consider that we will get a racemic mixture. Right? So I'm just going to put a little note right here. We'll get 1 stereocenter. Okay. Again, this secondary carbocation will undergo rearrangement. The OH will end up here. And this will become an ethyl group because we have a hydride shift happening. However, this will not be a stereocenter because these 2 groups are considered identical. This one is no stereoselectivity. Okay, now I think we can finally start drawing our products. So we want to add in the OH group at the more substituted carbon, and it's forming a stereocenter, so make sure to draw a racemic mixture. One way to indicate a racemic mixture is just to go ahead and draw one of the chiral centers or one of the enantiomers, and then draw just right plus enantiomer to signify that we also get the racemic mixture. Remember this one, we don't need to consider regioselectivity because it's symmetrical, and we are not forming a stereocenter, so we don't have to consider stereoselectivity either. This one is just a simple alcohol. And now this one's a little bit more challenging. We did form a secondary carbocation, which will undergo rearrangement. We'll end up with this carbon scaffold with a methyl here, but then this will become a stereocenter. 4 different groups attached, so we'll want to write plus enantiomer. Next, we'll form a secondary carbocation. It will rearrange, but we decided that would not become a stereocenter, so we don't need to consider stereoselectivity. So we can just draw it like this. Okay. So remember, you really do need to remember your mechanisms to be able to draw these products. It makes it a whole heck of a lot easier. Students who try to just memorize everything end up forgetting stuff on the exam because it's just so much to try to memorize. So it's better if you understand mechanistic rationale, right? How is the mechanism going and how does that help me draw products? Okay, the next reaction we're going to talk about is Markovnikov hydration, which occurs without rearrangement. That reaction is what is called the hydroboration oxidation reaction. And it gives the same hydration product as when we used H3O+. We just don't have to concern ourselves with rearrangement. Right? So what is different? Well, the mechanism is different. Right? We do not form a true carbocation intermediate. So rearrangement do not occur. All right, so let's go ahead and start drawing products. So really all of those same things we were considering before are still applicable right now, right? So what is getting added? Show. What is getting added across the double bond? It's still H and OH. We still have Markovnikov regioselectivity. We still need to worry about stereoselectivity depending on how many stereocenters are formed. The only thing we don't need to worry about is potential for rearrangement when you're using the hydroboration oxidation. Oh my gosh. Sorry. I don't know where I came up with that. Not, apparently my brain is on other things. This is oxymercuration. Demercuration. Good thing I looked at that again to be able to correct that error. So sorry about that. Okay, so we want to consider all of those things when drawing products. So this one, right? Do we need to consider regioselectivity? Yes, because this is not a symmetrical alkene. So we want to know that the OH is going to get added at the more substituted carbon, and it will form a stereocenter, so we need to make sure to draw the racemic mixture. Again, we don't have to concern ourselves with rearrangement. This substrate would not have rearranged anyway. So really the product is the same regardless of the reaction, the hydration reaction being used, either oxymercuration, demercuration, or acid catalyzed hydrolysis. So let's go ahead and draw that product in. So I usually use the second model because I think it's easier to draw in the product. So I'm just going to place this group on a wedge, making sure to also write plus En, or you can go ahead and actually draw in that product as well. Okay. This one, do we have to worry about regioselectivity? No, because it's a symmetrical alkene. We also don't have to worry about stereoselectivity because just like last time, we're not forming a stereocenter. And we also don't have to worry about rearrangement. So this is the same product as it was last time. Again, it will only be a different product if we did a rearrangement in the previous example. Remember, this one did rearrange, but in this case, it will not rearrange. So we don't have to consider rearrangements with this reaction. It is going to be a hydration. It will go Markovnikov, so the OH will end up here. And it will form a stereocenter, so we want to make sure to go ahead and draw that in. And draw in the OH up and also down. Let's look at this case. You'll get a secondary carbocation, and it will not rearrange because it's nice and stable and benzylic. So the OH will end up here. It will be a chiral center, so we want to make sure to draw into enantiomers. Lastly, here's our pi bond. The OH will end up on the more substituted carbon. That will become a stereocenter, so we want to make sure to draw that. This one is just there, and it's not being touched, so it just stays in the product. So that one does not change. You can just draw that in exactly as it is. And then note that we will form the Markovnikov product. So the OH will end up on the more substituted carbon. The hydrogen will end up here, just becoming a CH2 group. This would also, the other stereocenter will also form at that carbon. However, this one would not change. Right, so in this case, we have a mixture of diastereomers because of the existing chiral center, whereas in these three, we ended up with a mixture of enantiomers with only one chiral center, the product of those. Right? And this one, there is an achiral product, so we don't need to consider any stereochemistry. Let's do some multi-step synthesis. Provide a synthetic strategy for the following transformation. So recall that if you're starting with an alkene, you only have one option for your first reaction. Right? You must do radical halogenation. That is your only choice because that's the only thing we can do to functionalize an alkene. So from here, you might be tempted to do an SN1 reaction. And that is certainly possible, but I'm just going to kind of a little dotted line, right, to do SN1 with water. Certainly possible, but remember, we try to avoid SN1 reactions if possible because they commonly compete with E1, the E1 pathway, and we would get an alkene product as a mixture. So SN1, we'll make a little note of that, right? So SN1. And E1 occur, you have a mixture. So not just the desired product, but also some elimination products, an alkene. So how can we avoid doing kind of a reaction that gives a mixture? Well, perhaps we can do an alternative. Maybe we can do an elimination addition sequenced together. So if we did an elimination, we could get an alkene, right, followed by an addition. So that is one way to go from one functional group to another. It is this sort of elimination, addition, sequenced together. This is just a radical elimination. Okay, so how can we then do this elimination? Should we do E1 or should we do E2? Recall that E2 is usually the better choice because E1 often will give a mixture with SN1. So if we can do E2, that's better. In this case, we can use any strong base because we don't have to worry about regioselectivity because all of the beta carbons are equivalent. Right, so we're going to do E2. Right, noting that you don't have to worry about regioselectivity. So any strong base will work out well for us. We don't have to worry about SN2 because it's a tertiary substrate. Tertiary substrates don't undergo SN2 reactions. Okay, now we want to do the addition reaction. So we ask ourselves, what's getting added across the double bond? Well, we want a hydrogen added here, and then an OH added at the more substituted carbon. So this isn't just going to be any old addition. We need to add an H and OH. So we need to do a hydration. And we want it to be a Markovnikov hydration. So that the OH will end up on the more substituted carbon. Do we have to worry about rearrangement? No. The carbocation will be tertiary and it will not rearrange. So we'll just write, don't have worry about rearrangement in this case. Which means you have choices. You could use the cheaper H3O plus reagent, or you could use oxymercuration demercuration, and that would just be more expensive reaction, but would produce the same product. Okay. Moving on to the next page here. Let's move on to the anti-Markovnikov hydration reaction, which is the one that's actually called hydroboration oxidation. Notice that this reaction, not only do we consider regioselectivity because it is anti-Markovnikov, right? This is the regioselectivity. but the fact that it says syn only tells us that this reaction also has stereoselectivity. So lots to think about here. In the first step of this reaction, we have borane adding across the double bond. The H will end up on the more substituted carbon, and BH2 will end up on the less substituted carbon, which eventually converts to Br2. And then the boron is replaced by an OH group in the oxidative cleavage step, which is the second step here with sodium hydroxide and hydrogen peroxide. Notice that the hydrogen and Br2 end up with syn addition, which will only matter if you end up with a product with 2 chiral centers. In this case, we would end up with a product with 0 chiral centers, so we don't have to concern ourselves with the stereoselectivity when drawing the product. However, when we form 1 chiral center, we will always draw a racemic mixture. And when we form 2, in this particular reaction, since it's syn selective, we will want to draw in the H and the OH getting added from the same face, forming only the syn selective products. Okay, so question. Describe how the hydration in the above reaction is different from the previous hydration in C and D. Right, so we will write, so these conditions, right? Trying to think of how to write that. Give the anti-Markovnikov regioselectivity. Right, previously we were doing Markovnikov regioselectivity. Okay, so when you look at these reagents and you see the hydroboration oxidation reagents, ask yourself, what is getting added across the double bond? The answer, H and OH. This is a hydration reaction. However, regioselectively, we get the anti-Markovnikov product. So the OH gets added to the less substituted carbon. And then stereoselectivity is next. How many stereocenters are being formed? If 0, we don't consider stereoselectivity. If there's 1, we always draw a racemic mixture. And if there's 2 stereocenters, in that case, we want to make sure to draw syn selective products. That is going to be the case in this first reaction. We're going to have the H ending up here and the OH ending up on the less substituted carbon. That is going to form 2 stereocenters. So we need to make sure that the H and the OH get added across the double bond from the same face, which, because there's a methyl group at that top carbon, if I put the OH group on a wedge, that means that the hydrogen here also got added from the top, which pushes the methyl back, right? So you can add in the up hydrogen here if you want, or it can be left off. So we'll just draw it both ways, right? And then I'll just write this simplifies to and we also get the enantiomer. Make a note of that. That's the enantiomer, which is the exact opposite at both chiral centers. Right, but these are both syn selective products. Next, again, we're adding H and OH across the double bond. It's going to go anti-Markovnikov, so the less substituted carbon will get the OH group. We are not forming any stereocenters in this case. So with no stereocenters being formed, we don't have to concern ourselves with stereoselectivity. Let's look at this one. Again, H and OH is getting added across the double bond. The OH gets added to the less substituted carbon in this case, and we will not be forming any new stereocenters. So we can just go ahead and sketch that in with the OH on the less substituted carbon. No new stereocenters formed, so we just need to draw it this way. Let's look at this one. Again, H and OH is getting added across the double bond. The OH will get added to the less substituted carbon. That's going to make both of these become a chiral center. We would want to make sure to draw that in. So if my OH get added from the top, that would push this methyl down because the hydrogen also got added from the top. And we also get the enantiomer. From when the OH and H get added from the back, from the bottom. Okay, maybe take some notes here. Right. So what's the answer to question number 1? What's getting added across the double bond? H and OH. The answer to question number 2, regioselectivity. Yes, this reaction goes anti-Markovnikov. Stereoselectivity. And yes, it is syn selective. Do I have to worry about rearrangements? No, because this mechanism does not go through a carbocation intermediate. Right? Make a little note. Mechanism does not involve a carbocation. So we do not have to think about rearrangements in the hydroboration oxidation reaction. Moving on to the next part, provide a synthetic strategy for the following transformations. So it looks like they pretty much start out similarly, where we're starting with an alkane. And at that point, the pathway is probably divergent. So recall, when you're starting with an alkene, how many options do you have for your first reaction? You only have one. Right? You have to do radical halogenation. That's going to be the same first step in all 3 pathways. And I know that because I'm starting with an alkene, so I only have one choice. I have to do radical halogenation. And my bromine will go on the most substituted carbon. Okay, from there, it looks like I need to do an elimination to get an alkene. So we're gonna, again, do the same second step. To get the alkene here. Right, so what is going to work to do elimination? So this is a Zaitsev elimination. So I want to use a small, unhindered, strong base to do my E2 reaction to get this Zaitsev product. So sodium hydroxide is a good choice, or sodium methoxide or sodium ethoxide are also considered small, strong bases. All right, so now some of these we can get directly from this alkene, and then others we might need to do a few more steps. So from this point, it looks like we need to add H and OH across the double bond. We want it to go anti-Markovnikov. And we are forming a stereocenter. However, nothing is indicated, so it's probably a racemic mixture. It will be in all cases anyway. Right, so in order to get to this product, which again will be formed as a racemic mixture, right, we are going to do hydroboration oxidation, because that reaction gives us our anti-Markovnikov hydration product, which is what we are going for. What this one, it looks like we are not able to get to here all in one step. However, we can get to this in one step. So we'll go ahead and write that one out as well. Okay, so we'll do, how could I get from here to here in one step? This is an addition reaction. Again, we need to do a hydration because we're adding H and OH across the double bond. This one is going to go Markovnikov. I have two choices when I want to do Markovnikov hydration. I can use H3O plus to do acid catalyzed hydration, or I can do oxymercuration demercuration to get the Markovnikov hydration product. Since I don't have to concern myself with rearrangement in this case due to the formation of a tertiary carbocation, then I can go ahead and just use the cheaper H3O plus. Right, but I'll just write or. You have the option of doing oxymercuration demercuration. So those can be obtained with one step, and then the last one cannot fit on this paper, unfortunately, so I'll just continue on. But I want to do, how am I going to get from here, which is where I'm at right now, right, to having the OH group over here. So a couple of different ways you could potentially do that, but I think we want to do an addition elimination sequence. Right? If we can add in a leaving, something that's a good leaving group, here, like a bromine, then we would be able to eliminate that good leaving group, right, to form the alkene that's moved positions. And then we'll be able to do an addition reaction to get the OH in the position that we want. So that's going to be our strategy here. Now we just need to fill in the different reagents that we would want to use. So what are we adding across the double bond? H and Br. Right, so already I'm just going to write HBr. But then I'm going to ask myself, do I want this to go Markovnikov or anti-Markovnikov? Looks like the halogen is getting added at the less substituted carbon, so I want to do anti-Markovnikov hydrohalogenation. So I'm adding peroxides. Next, I want to do an elimination reaction to get the Hofmann product. So in that case, I want to use a bulky base to get that Hofmann product. Lastly, I want to do an addition reaction. Now I'm adding H and OH across the double bond. This is a hydration, and I want it to go anti-Markovnikov. I need to remember the conditions for anti-Markovnikov hydration, and that is hydroboration oxidation. So you need to know your reactions and what they do in order to be able to sequence them in these multi-step synthesis problems. All right, let's look at the next reaction, which is hydrogenation. Hydrogenation involves hydrogen gas and some sort of catalyst. Common ones are palladium on carbon or platinum, but other metal catalysts can be used as well. So what atoms are getting added across the double bond in a hydrogenation, H and H, right? So when you have two of the same, right, there isn't any regioselectivity to consider. That only happens if the groups that are getting added are different. Why aren't the hydrogen atoms shown in the product? So these two that got added, I don't see them, right? And just put in line structures. It is common to not draw hydrogens attached to carbon. So we know they're there. We know that the hydrogen is up, up, down, down, but we don't draw them in. However, because those groups did get added, the other groups became on two wedges or two dashes because of the syn stereoselectivity. So it's important to recognize that hydrogenation has syn stereoselectivity. That's only going to be important if you are generating two chiral centers. Then you need to concern yourself with this. Not generating any chiral centers, then you don't worry about it. If you're generating one, it's always a racemic mixture. But this one does undergo syn selectivity, which is important if you're drawing two stereocenters. So let's predict the product of the following transformations. So we have 3 different double bonds here that would all get hydrogenated in this reaction. So they get reduced to single bonds. And there aren't going to be any stereocenters. So we don't need to consider stereoselectivity. Okay, so no stereocenters. Okay, and all alkenes are reduced. Because there's no way to control, no easy way to control the amount of hydrogen gas present, right? So there's always going to be excess hydrogen gas present. The next one, we will reduce this double bond and it will be syn selective. So you could think of the H as being up, up or down, down, which would of course push this methyl either up or down. However, that does not form a stereocenter. So we do not need to concern ourselves with drawing stereoselectivity. Right? Again, no stereocenters formed here. This one, though, this is a little bit tricky because they're talking now about deuterium. Remember that deuterium is kind of like labeled hydrogen. It's just a different isotope of hydrogen, and they draw it so that you can clearly see where the hydrogen gets incorporated into the molecule. So we want to draw that, but both of these are going to become chiral centers. So in this case, we're going to have 2 new stereocenters. We want to make sure to draw that syn selectivity. So if both hydrogens get added from the bottom, that would push the other groups up. And it's also possible, equally possible, for both hydrogen atoms to get added from the top, which would push these groups down. Oh, and sorry about that. I guess I should have added in those deuteriums. If it was hydrogen, we could just leave it like this. At deuterium, we should add in. Those are both getting added from the back, or both getting added from the top. Okay, provide a synthetic strategy for the following transformation. So we want to get an alkane, and we just learned a reaction to provide us with an alkane. It is a hydrogenation reaction, which is the reduction of an alkene to an alkane. So we could target an alkene as our key intermediate, or key synthetic intermediate, which is not an intermediate in a mechanism, but intermediate in a synthetic pathway. And then we could hydrogenate to remove that double bond. So H2 and either platinum or palladium catalyst, right, will do a hydrogenation. Then we just need to do an elimination reaction to get this alkene. There is only one beta carbon, so we don't have to concern ourselves with regioselectivity. However, in this case, I always prefer to use a bulky base, because if I use sodium hydroxide, that will do SN2 as the major pathway, right? So we'll make a little note here. Use a bulky strong base to avoid SN2 as a competing reaction. Remember, SN2 predominates on primary substrates, except if the nucleophile is too bulky. So to prevent SN2 occurring, we want to do E2, right? Then we're going to use a bulky base, and it's not because we care about Zaitsev-Hoffman. There is no Zaitsev-Hoffman in this case. There's only one beta carbon. It's just to prevent substitution. Okay, moving on to the last page of the activity here. This feels like a long one today. We are going to fill in the empty boxes below with the proper structures or reagents. Consider stereochemistry whenever applicable. Okay, so remember, when we are approaching problems like this, we want to ask ourselves those three questions. What is getting added across the double bond? Right, so remember the 3/4 questions, really, if you're also thinking about rearrangements. So what is getting added? Remember our questions, we'll write these in. What is getting added across the double bond? Right? Do I need to consider regioselectivity? What about stereoselectivity? And maybe you almost call it 4 questions. What about rearrangements? Okay, so when we're answering these questions, right, we're saying, what is getting added across a double bond? Well, with H3O plus, we are doing a hydration, so we're adding H and OH across the double bond. Sometimes, because these are different, right, there could be regioselectivity depending on if the alkene is symmetrical or not. The regioselectivity, in this case, is Markovnikov, which means that the OH will end up at the more substituted carbon. This will not form a stereocenter, right? So we do not need to worry about stereoselectivity. We can just place our OH here. These conditions do potentially do rearrangement, but not on a tertiary carbocation that will be formed here. All right, the next question is, again, what is getting added across the double bond? So you can see that I have a hydrogen getting added here and a hydrogen getting added here. We're adding H and H, right? So in this case, no regioselectivity, right? But we do have syn stereoselectivity. So that's important here. So this is a hydrogenation reaction. Maybe we should be writing in the reactions. Good reminder. This is Markovnikov hydration. Right, and then we're going to do acid catalyzed. This one was a hydrogenation. Okay, looking at this next example, what is getting added across the double bond? So we are going to be adding in this case, deuterium and deuterium. And remember, we don't consider regioselectivity when the group is the same, but this is potentially syn selective reaction. This is another hydrogenation. So if we're getting a hydrogen here, this will not be a stereocenter. And the hydrogen here will be a stereocenter. So in that case, we have one stereocenter. Right? So we really don't have to worry about the syn selectivity. That's only one stereocenter. So always. So let's go ahead and draw in that product. So if the hydrogens both got added from the back, then this would be up, right? Or we could also get the plus the enantiomer. All right, the next one. This is a different way of writing BH3THF. They haven't included the THF solvent here, but this is just diborane instead of borane. And that's where borane comes from. You can make it from diborane. So this is just a hydroboration oxidation, which if we remember, is a hydration reaction. So we're adding H and OH across the double bond. And it has syn selectivity, and it goes anti-Markovnikov. So lots to remember here. Okay. So what are we adding across the double bond? We are adding H and OH. Remember, it is going anti-Markovnikov. Right, and potentially syn selective, although let's look and see how many stereocenters are being formed. So if it's going anti-Markovnikov, the OH will end up on the less substituted carbon. So this will become a chiral center and this will become a chiral center. So we are actually forming two stereocenters. This is important now to draw that syn selectivity. So we're going to go ahead and draw that in. So we have, remember, if both hydrogens get added from the top, then that would push, if the hydrogen and OH get added from the top, that pushes the methyl down, right? And both the H and that OH got added from the top. We would also get the enantiomer here. From when the H and OH get added from the back. Moving on to the next reaction. What is getting added across the double bond? We have H here and OH there. So this is another hydration reaction. And make some notes here. You're adding H and OH. It is going to go Markovnikov because the OH is getting added to the more substituted carbon. And no stereoselectivity at all. We have not indicated that this technically is a racemic mixture. So how do we do this? Well, there's two conditions to do Markovnikov hydration. You can use acid catalyzed hydration with H3O plus or oxymercuration demercuration. Oxymercuration demercuration is useful when you're concerned about rearrangement. And the secondary carbocation that would get formed here would rearrange, right? So this substrate, secondary, tertiary rearrangement, right? And then so to avoid that, which we want to avoid because we're not showing the rearranged product. We want to avoid rearrangement here with this Markovnikov hydration. So we want to use oxymercuration, demercuration. Okay, so the conditions for that are mercuric acetate, water, and sodium borohydride as the second step. So with this substrate here, what would get added across the double bonds? We're adding H and Cl. There's no peroxides mentioned, so this will be Markovnikov, regioselectivity, and there's no stereoselectivity in this reaction. So, but that doesn't matter because we're not even forming a stereocenter. The chlorine will go here, and that will not be a stereocenter. You can just draw it like we see it with the chlorine there, right? This one is achiral. Just like this one up here was achiral. Okay. So let's write in the reaction though. This is a hydrohalogenation reaction. Next, it looks like we want to do another hydrohalogenation reaction because I noticed that we need to add H and Br across the double bond. But it looks like this one is going anti-Markovnikov because the bromine got added to the less substituted carbon. So in order to do that, we're going to use HBr and peroxides. So we'll make a little note. This one is Markovnikov. Anti-Markovnikov. All right, last reaction. This one wants the starting material. We're doing a hydroboration oxidation. So what will have gotten added across the double bond is H and OH. Right, this one will have gone anti-Markovnikov. And hydroboration oxidation reactions are syn selective. So all of that is true with this product, plus it did not mention in an enantiomer, but of course we would get one. Even with the syn selective, we get the down up. In this case, we want the alkene reactant. going to have a methyl here and a double bond there. Note that we don't put this dash in. Right now it's sp2 and trigonal planar, so everything's in the plane attached to these two carbons, so no need for a dash or a wedge. Right, this is hydrofluoration oxidation. All right. So hopefully you've gotten the idea of how we approach these problems, right? Ask yourself those questions, try to remember the details of the reaction, regioselectivity, stereoselectivity. Is it one of the reactions that goes through a carbocation intermediate and I have to concern myself with rearrangement? All of that stuff needs to be asked to be able to approach these sorts of problems. And I really encourage you guys to practice with lots of problems from your book.